Hi, this is the second video in this little video series on the matrix groups SO2 and O2, the second special orthogonal group and the second orthogonal group. And in the first video, we looked at just a particular rotation matrix which belongs to the special orthogonal group, and that group, of course, is a subgroup of the orthogonal group, and so this matrix also belongs to O2. And in this video, we're going to look at a general rotation matrix that's described in terms of sines and cosines for an angle theta, which could be any angle you like. Before I get to that, I want to make a remark, and that is that when we're talking about these matrix groups, there's really an implicit R, so this is for real numbers here. So that tells you that the entries in these matrices that we're looking at here are real numbers as opposed to coming from some other object, like the rational numbers, for example. Now, and so what this notation means, this just means special orthogonal, and then that it's the second one, so it's 2 by 2 matrices. And then the semicolon just means, well, it's just a way of separating this information from this information, and then the fancy-looking R here just means for the real numbers. And the reason I point this out is because if we get around to talking about the unitary groups later, for instance, there's a special unitary group, and so this will be, we could take the third one, for example, and this will implicitly mean that it has the complex numbers there. There will be a different field of numbers. And you could also take, and of course, you can do the same thing here for O2. It's really the real numbers that you're talking about in that context. And this is usually the case when I write SO2 or O2, that you mean that. But you could look at matrices with just rational entries, for example, and those would form a subgroup of the one with the real entries. So there is a source of the particular numbers that are appearing in these matrices. You really do have to specify that somehow, and up to this point I've just been assuming that they're real numbers. And we will continue to assume that when we're looking at the special orthogonal and the orthogonal group. That's usually the convention. If we get to unitary groups, then of course things will be different. So let's move on now. So last time, I just want to recall this explicitly. Last time we looked at the rotation matrix. Well, I'm not going to write rotation. I'm just going to write matrix because I'm about to write what it does. So we looked at the matrix, and it's that one over there, square root of 3 over 2 minus 1/2 square root of 3 over 2. And we saw that this, well, I say we saw, I didn't prove it, but we saw informally. So I'll say informally that this matrix rotates column vectors, which we could call a general column vector AB like I did before, by pi over 6 radians. And so if you want to say degrees, this is 30 degrees, counterclockwise in the plane. R2. And so if you draw a picture of this, what you would see is we have a coordinate system for the plane. This here is the plane, and we have x going this way and y going this way. And so if I have a vector AB, and you remember what this meant, it meant an arrow that points that way. This is a right angle. This distance is A. This distance is B. So that vector there is just this AB here. And we saw that what this matrix does when you multiply this vector on the left by the matrix. So if I put the matrix right here, what it would do is it would take that same vector and it would rotate it this way through an angle of pi over 6. And we did a few examples to see that it really does that. We didn't prove that it does that in general. Now, what I want to do while this is still written here is I want to pull this down here. I want to look at this and I'm going to write down here another way of expressing these numbers here. And that's where these sines and cosines are going to come in. So you can write this here as, see where the sines and cosines are? This is cosine pi over 6. And then minus sine pi over 6. And then sine pi over 6, cosine pi over 6. So that's what these numbers here are really saying. If you worked out what the sines and cosines were of this particular angle, that's what this matrix would be. And so this is, you know, what we're going to see is that if I take any angle, which I'm going to call theta, and I put it in there for this pi over 6, you know, if I take any angle and I put it in there, there, and there, and there, then this will do the same thing, except now it will rotate by theta radians instead of just pi over 6 radians. Now, before we look at another example of this or talk about it in any more detail, I want to do just like a 2-minute trig review for you, because I don't know how up to speed all of you are on your trigonometry. It's a very diverse class. And so what I'm going to do is so take that matrix there, I'm going to write an equal sign, and I'm going to rewrite what I had there, which was cosine pi over 6 minus sine pi over 6, and then sine pi over 6 cosine pi over 6. And I just want to remind you what this means. So this is a trig, this is a little trig review. So if I have any right triangle, and I'm just going to draw a big right triangle here. And so right triangle, there's a right angle there. And so there's an angle here, which I will call theta. And you have what you're used to naming these as the opposite side, the adjacent side, and the hypotenuse. That's this side here. And that's a little messy, but we'll live. So you remember that. So for this angle, what the sine of theta means, so this means, so this is a definition. It means it's a fraction. It's the opposite side over the hypotenuse. Of course, in the cosine theta, this just means the adjacent side over the hypotenuse. So these are both just numbers. Now the hypotenuse is the biggest of these sides. So the largest value that these could possibly have is 1, and that would get, you know, for instance, if it becomes a very steep, tall triangle like that, then here the opposite side is almost as big as the hypotenuse, not quite. But you're getting the sine here. Here, if that's theta there, the sine theta is almost, I could put kind of a squiggly equal sign. It's close to 1. It's not quite 1. And so on. But that's what these are measuring, just to remind you that. And so, in particular, if I have now the unit circle, so this is a circle that has radius 1, so this is unit circle. This is oftentimes called S1. Now you see it here, and you see it down here again. This means 2 copies of S1, so that's 2 circles, 1, 2 circles, and we'll see how that comes into play later. But in this case, if I have some angle, theta here, well then, here the hypotenuse is 1. So in this case, the adjacent side is just cosine theta, and the opposite side is just sine theta. Because sine theta means whatever the opposite side is over the hypotenuse, but the hypotenuse is just 1. So it's just the opposite side, and similarly with the adjacent side there. Now that's what you're seeing in this case here. And what you're seeing, and I'm going to erase this and redraw it with the particular case that we had here. So I'm going to have unit circle again. Let's see if we can put a unit circle on here. See, now we have, in particular, we have this angle pi over 6. It's kind of a messy pi. Let me draw that a little bit more neatly. That's pi over 6. And so this is one of you, if you remember your trig, this is one of your special triangles where you'll get the cosine of it. This side down here is going to be square root of 3 over 2. And this side over here is going to be 1/2. Now, it's rotated less than halfway from the x-axis up to the y-axis, if this is the x-axis and this is the y-axis. So you expect this side to be longer, because this side starts out as being that whole unit length when the arrow starts here, and then as you rotate it up to here, this side is getting shorter, but it still is going to be longer than this side because it's rotated less than halfway up when you get there. So you can recognize this particular matrix that we used before as being of this form, and we saw that when we take a matrix of that form that it does indeed rotate any vector then in the plane by that pi over 6, or 30 degrees if you want to describe it that way. So what we want to say now is that, well, I guess I'll erase all this. So that was last time. And so now what we're going to do is generalize this. And that is the matrix, and it's that one there, which I'm going to recopy here. So there's a cosine theta, a minus sine theta, a sine theta, and a cosine theta. This matrix here rotates column vectors AB by an angle of theta radians counterclockwise in the plane. Now, even though I just showed you what sine and cosine are again, or reminded you what sine and cosine are, you might be less comfortable with this expression because it doesn't have numbers in it. It's something that's general. It has the symbols in it, and so it might be kind of hard to get as much of a handle on that. So I want to do an example where we're going to start out with the same vector that we rotated first with the concrete specific rotation matrix, that one here. And we're going to look at rotating, so we're going to rotate the vector, and it's going to be this one, 1, 0. And this is the one that we looked at before, and you saw how this looked. If this is x, this is y. And so this was just the vector that starts out at the origin, and it goes a distance of 1 in the x direction, and has no y component to it, because here, well, the y component is 0 here. So what we're going to do is we're going to take that matrix, cosine theta minus sine theta, sine theta, cosine theta. We're going to use it to transform this vector. So we have matrix multiplication again. This row, there's only one column, so I'm pairing the cosine with the 1 and the minus sign with the 0. So that's going to give me a cosine theta here. And then the sine theta goes with the 1, and the cosine theta goes with the 0. So this is going to be a sine theta here. Now see what this did. Even though you don't know what the angle is, you can still see in terms of the unit circle thing that I drew you before what this is doing. You have, here you have, let me fix this just a little bit. I'm not drawing the whole picture now because I don't need the part over here. So I'm just drawing part of the unit circle. So this is part of the unit circle that goes like this, and then it continues on. Well, what happened is we had this vector of length 1. I'll tell you what, I'm going to cheat. I'm going to make this one look a little bit longer so that it matches what this is, okay? So I'm going to extend this out, and I'm going to have this vector here go up to right there. See, I want it to be the same, look the same length as that one there. So we've taken this vector now, and we've rotated it by, this is what it's supposed to do. It's supposed to rotate this by theta radians, where I haven't told you what theta is, but I don't have to, because you know this is the unit circle, and so this is a right angle, and so you know that the adjacent side, whatever that angle is, the adjacent side is cosine theta, and the opposite side here, let me get rid of this, is sine theta. And that's exactly what vector you got. So you know it's doing the right thing. You can see it's doing the right thing, even if you don't know exactly what the theta is. So this is the general form of the rotation matrix. Now, I think what I'll do is I will do one more example of this with numbers. And the reason for doing this is we're kind of coming from the other direction. See, before I gave you a matrix with numbers, and then I showed you after the fact how it could be seen in terms of sines and cosines. Here I'm going to give you the angle first, and then we're going to think about the sines and cosines of that angle, and we'll get the numbers out of it. So, example, if we want to rotate by an angle of pi over 4 radians now. So if you like, this is 45 degrees. If you like to think of it in terms of degrees, counterclockwise, in the plane, we should use the rotation matrix. Which one? Well, it should be the one that's given by that formula. Cosine, now the theta is pi over 4, so this is going to be cosine pi over 4 minus sine pi over 4 sine pi over 4, cosine pi over 4. And we can tell what these numbers are. And if you don't remember off the top of your head, you can look in a trig book, or you can, look for cosines and sines of special angles online or something. This one is square root of 2 over 2. That's the cosine here. Minus sine, this is minus square root of 2 over 2. The sine, this is square root of 2 over 2. And then this is square root of 2 over 2. See, they're all the same size. The only difference is there's this minus sign because of the minus sign here. And that makes sense if you think about it, what the 45 degrees is, or the pi over 4 radians. See, that's where you've gone exactly halfway. The rotation, you've rotated exactly halfway. This is pi over 4 from the x-axis up to here. So when you do that, let me write this a little bit more conveniently. When you do that, so this is pi over 4, and I draw this right triangle. Well, this side ought to be exactly the same as that side just because of symmetry, because you've rotated exactly halfway up. And they are. These sides are both square root of 2 over 2, square root of 2 over 2. So that's what matrix you use. And now let's just check with an example that this matrix does what you expect it to. So check the action of this matrix on the vector. And now I'm going to choose a special vector, which is square root of 2 over 2, square root of 2 over 2. And the reason I'm choosing this one is because you will know before I tell you what the matrix should do to it, right? Because this one is pointing, it's going halfway, it's rotated halfway from here up to here. And so if this matrix does what I told you it's supposed to do, then it ought to take that vector there and rotate it the rest of the way straight up. So this is just a recopy. It should take this one, and it should send it over to the one that just has a 0 x component and a 1 for the y component, because it should be the one that goes straight up. Now let's see if we can fit this down here, fit this computation. So let's write the matrix, square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, square root of 2 over 2. And we're multiplying it by this vector here. Square root of 2 over 2, square root of 2 over 2. Let's see what it does. Well, the first component, the top component here, we have square root of 2 over 2 times square root of 2 over 2. Now the two square roots together give you a 2. The 2's together give you a 4. That's 2 over 4. So that's 1/2. And then same here, except there's a minus sign. Square root of 2, square root of 2, that gives you 2. The 2 and the 2 give you a 4. 2 over 4 gives you 1/2, but there's a minus sign. Those cancel, so there's a 0. And then here, what do we get? Well, the first one, we get square root of 2 times square root of 2 in the numerator. That's giving us 2 over 4. That's 1/2. And then here we get another 1/2 from the same thing, so we get 1. And that's exactly what we expected to happen. So anyway, you can test it more if you want on other vectors or whatever and see that it does the same thing. But that gives us, I think, enough of an idea of what this general rotation matrix does. So in the next little video, we will talk about why do the rotation matrices form a group.